it's important to understand that this mole that we're talking about represents a unit of measurement. Just like, say, a dozen. If I said a dozen, you would think, oh, 12 of something. What if I said a gross? Do you know what a gross is? A gross is actually a dozen, or 144 of something. So a gross of anything is 144 of that anything. A ream represents 500 of something. Usually we talk about paper in those terms. So just like those other terms, the term mole has an equivalent amount. That amount for us is 6 followed by 23 digits. To put it in scientific notation, 6.022140076 times 10 to the 23rd power. It's an enormous number, but you got to realize we're talking about extremely tiny things, so it takes an enormous amount of them to do anything of consequence. By the way, we can abbreviate a little bit and just call it 6.02 times 10 to the 23rd. You might be wondering though how we actually got that number and how it equates to 1 mole of something. The concept of the mole has actually been around for a while, but here's how that number came about. It starts with a guy named Michael Faraday, a brilliant scientist who did a lot of work with electricity. In fact, he came up with something called the Faraday constant. The Faraday constant is a number that's equivalent to 1 mole's worth of actual charges from electrons. You get it? So if you took 1 mole of electrons and put their actual charges together, you would have the same number as the Faraday constant. The Faraday constant is about 96,485.332, yada yada yada. So that came first. So we had this number from Faraday, which was a mole's worth of charges, but we didn't know what one individual charge was to know how many of them were in there in the first place. Fortunately, along came Robert Millikan. Robert Millikan performed his oil drop experiment, and he was able to determine the actual charge. Not the relative charge, not the -1 that we use, but the actual charge on each individual electron. He determined it to be 1.602 times 10 to the -19th coulombs. A coulomb is a unit of charge. So when we took Faraday's constant and divided it by the charge on a single electron, it gives us, ta-da, 6.02 times 10 to the 23rd. And now we know that that represents 1 mole of anything, really. It could be atoms, it could be molecules, it could be marbles. I hope not. A mole of marbles would kill us all. We would be buried under about 3 miles of marbles. So let's keep it to something really small like atoms and molecules. How about that? After this number was determined, it was given a name. It was given a name in honor of a scientist whose name was Amadeo Avogadro. Now, Avogadro didn't determine this number himself, but in his honor, this number was named for him. So, 6.02 times 10 to the 23rd is known as Avogadro's number. We can even use Avogadro's number to explain the relationship between an atomic mass unit and the gram. It works like this. 1 atomic mass unit is equal to 1 over 6.02 times 10 to the 23rd grams. So watch this. Let's say we have a carbon-12 atom. A carbon-12 atom has a mass of 12 atomic mass units. But how much would that be in grams? Well, it would actually be 12 divided by 6.02 times 10 to the 23rd grams. So now, what would the mass of 1 mole of carbon-12 atoms be? Again, 1 carbon-12 atom would have a mass of 12 divided by 6.02 times 10 to the 23rd grams. Watch what happens when we have an entire mole of carbon-12 atoms. If 1 carbon-12 atom is 12 divided by 6.02 times 10 to the 23rd grams, and we have 6.02 times 10 to the 23rd of those carbon atoms, 1 mole's worth of carbon atoms, then the total mass of 1 mole of carbon-12 atoms is 12 grams. Isn't that cool? So the 6.02 times 10 to the 23rd number allows us to have the same magnitude of mass whether we're talking about atomic mass units or grams. Using the values on the periodic table, that means that your average carbon atom is going to have a mass of 12.011 atomic mass units, or an entire mole of carbon atoms is going to have a mass of 12.011 grams. That's cool. An average sulfur atom will have a mass of 32.066 atomic mass units, But 1 mole of sulfur atoms, or 6.02 times 10 to the 23rd sulfur atoms, will have a mass of 32.066 grams. Just to make sure we've got this, if I have a scale that measures in grams and I have a pile of sulfur atoms, and I had atomic tweezers that allowed me to take one at a time, if I counted out 1, 2, 3, all the way up to 602 sextillion, or 6.02 times 10 to the 23rd, that scale would say I have a mass of 32.066 grams. The same number that's on the periodic table. That's the beauty of Avogadro's number. Now, in the same way that a dozen eggs has a different mass than a dozen roses or a dozen donuts, 1 mole of carbon atoms is going to have a different mass than 1 mole of sulfur atoms, or 1 mole of phosphorus atoms, or 1 mole of oxygen atom. They'll all have different masses. They all have the same quantity, but different masses. 6.02 times 10 to the 23rd carbon atoms has a mass of 12.011 grams. But 6.02 times 10 to the 23rd oxygen atoms has a mass of 15.999, or let's just say 16 grams. Because of that, we can actually calculate what we call molar mass, the mass of 1 mole of a particular compound. Take, for example, the molar mass of carbon dioxide. What would the molar mass of carbon dioxide be? Well, it's as simple as adding together the molar masses of carbon and oxygen, respectively. In this case, we have the molar mass of carbon, which is 12.01, and the molar mass of oxygen, which we'll just call it 16. So we have the carbon and 2 oxygens, which means we have 12.01 plus 16 plus 16. We do the oxygen twice since there are 2 oxygens in carbon dioxide. That gives us a total mass of 44.01. In other words, the molar mass of carbon dioxide is 44.01 grams per mole. Let's try another one. How about magnesium chloride, MgCl2? See if you can pause the video and calculate the molar mass of MgCl2. Like we did with carbon dioxide, we simply take the molar masses of each element involved. Magnesium's molar mass is 24.3 grams per mole. The molar mass of chlorine is about 35.45 grams per mole. So when we add the 24.3 for magnesium, the 35.45 for one chlorine, and the 35.45 for the other chlorine, we get a total mass of about 95.2 grams per mole, the molar mass of magnesium chloride. Remember that we're talking about 1 mole's worth of that compound. So 1 mole of carbon dioxide molecules, 6.02 times 10 to the 23rd carbon dioxide molecules, has a mass of 44.01 grams. 1 mole, or 6.02 times 10 to the 23rd formula units of magnesium chloride, has a mass of 95.2 grams per mole. So let's try a calculation then. How many grams of lithium are found in 3.5 moles of lithium? Remember, that number that's underneath the lithium is the atomic mass, but it's also the molar mass. So 1 mole of lithium is going to have a mass of 6.941 grams. We can simply multiply 3.5 moles by the molar mass, 6.94 grams per mole. In doing so, the mole units cancel and you're left with grams. So in 3.5 moles of lithium, we have 24.3 grams of lithium. We can also go the opposite direction. If you have 18.2 grams of lithium, how many moles of lithium do you have? Remember that for lithium, the relationship between moles and mass is 6.941. 6.941 grams in every mole. So in this case, we're going to take the mass that we do have and divide it by the molar mass of lithium. 18.2 grams divided by 6.94 grams per mole. When we arrange it this way, the gram units cancel and we're left with moles. Performing the calculation gives us 2.62 moles of lithium. So we can go from moles to grams or grams to moles simply by knowing the molar mass of the substance we're working with. We can do the same thing with Avogadro's number. How many atoms of lithium do we have in 3.5 moles of lithium? Remember that 1 mole of anything is 6.02 times 10 to the 23rd. So there are 6.02 times 10 to the 23rd lithium atoms in 1 mole of lithium. That means that we'll end up multiplying the moles that we have by Avogadro's number to get the actual atoms of lithium. When we arrange it this way, the mole units cancel and we're left with atoms. Performing the calculations, we have 2.07 times 10 to the 24 atoms. We can go the opposite way as well. If we have atoms or molecules and we're wanting to know how many moles we have, we would simply divide by Avogadro's number. To make this a little bit easier to understand, I designed this diagram. It's a map of what I like to call Molopolis and surrounding suburbs. We have Particle Town and we have Grahamsburg. We also have Leaderville, but we're not going to visit Leaderville just yet. We'll visit Leaderville later when we talk about gases. To get to Particle Town, I have to take Avogadro Boulevard. Avogadro Boulevard, of course, has the number 6.02 times 10 to the 23rd. So if I'm going from Molopolis to Particle Town, I have to multiply by Avogadro's number. And if I'm going from Particle Town back to Molopolis, I have to divide by Avogadro's number. You'll notice that down south we have Grahamsburg. To get from Molopolis to Grahamsburg, I have to multiply by the molar mass. To find the molar mass, I'll simply use the periodic table. To go from Grahamsburg back to Molopolis, I have to divide by the molar mass. You see how it works? Using our new map, let's perform a calculation going from Grahamsburg all the way to Particle Town. Now I have to tell you, there's no bypass to Particle Town from Grahamsburg. We have to go through Molopolis. How many atoms of lithium are found in 18.2 grams of lithium? Where am I going? I'm going to Particle Town. Particle Town, atoms or molecules, right? Where am I coming from? Grahamsburg. I have 18.2 grams of lithium. I'm going to use two conversion factors here. One going from grams to moles, and the other going from moles to particles, atoms in this case. I start with my 18.2 grams, and my first conversion factor will take into account the molar mass of lithium. 1 mole of lithium equals 6.94 grams of lithium. So essentially, I'm dividing by the molar mass, aren't I? That's my first calculation. The second calculation, going from moles to particles, means that I'll use Avogadro's number. In this case, I'll multiply by Avogadro's number. In other words, 6.02 times 10 to the 23rd atoms of lithium will be found in 1 mole of lithium. And again, when I arrange it this way, the mole units cancel and the gram units cancel, leaving me with atoms. Now I simply multiply all the tops together and divide by all the bottoms combined, and I get 1.58 times 10 to the 24th atoms of lithium. That's how many atoms of lithium we find in 18.2 grams of lithium. Here's a couple for you to try for homework. Number 1, how many moles of methane, CH4, do you have in 55 grams of methane? Remember, to find the molar mass of methane, you can add molar masses of the respective elements together. And number 2, how many molecules of carbon dioxide, CO2, do you have in 68.7 grams of CO2? So there's two calculations there, right? You can put your answers for both on the LMS. That's all we're going to do for this video. Today we talked about Avogadro's number and how we equate it to 6.02 times 10 to the 23rd of anything. For our purposes, atoms and molecules and so forth. We also talked about the concept of molar mass, how we can use the masses on the periodic table to determine the mass of 1 mole of an element or 1 mole of a compound. Then we introduced the Molopolis map, how you can use it to make your computations from moles to grams, grams to moles, moles to particles, etc. I hope this has been helpful to you and will assist you in your understanding. If I can help you in any other way, please let me know. Give me an email. Until next time, God bless.